Welcome back, everyone. This is Thursday evening in California. It is our fourth theory session. We'll start by reviewing in a very condensed form what we have learned so far in the previous week. And then we'll move on to the new topic. The topic for this week is classification. How do you create algorithms that can classify inputs into various categories or classes, for example, cats and dogs. So with that background, let's start with a quick review of what we have. Now, last week we did regression. Regression is essentially, one way to think of it is, it is a machine that can take inputs and produce a number. A vector goes in, a point in a vector space goes in. That's a more abstract definition. And then a feature vector. And then what it produces is a number as output. Examples are the entrepreneur, how much ice cream is he likely to sell on a given day, given the temperature, right? And if you bring in multiple variables, you can say temperature, wind speed, day of the week, whether it's weekend or not, and many other factors. So then you are creating a multidimensional feature vector. Okay. We have been taking that approach. Now I'm going to give you a slightly different geometric intuition to it. And this will capture the gist of all that we have learned in regression. So try to visualize this. Imagine that you have a sheet of, this aluminum foil that we use to wrap food in. So you have just taken it out. It's completely planar, right? Now, imagine that suppose there are two variables there, the wind speed and temperature, and you're trying to predict as a vertical axis, the horizontal two axes are wind speed and temperature, and the vertical axis of the data is the amount of ice cream that you sell. You have data. Now, if the data truly has a linear relationship, what you will find is that your solution will go through the data. It will be a plane. It will be like your aluminum foil, okay? That will be going straight through the data. Are we together? When it is a plane, then you call it linear regression. But if it is curved, then you call it a surface. It's no more a plane. It's no more linear. So in general, the definition of a surface is that at any given point, locally, it looks, we only deal with, well, the word that we often use here in this field is manifold. It's an embedded manifold, which is a fancy way of saying that if you look locally, it looks Euclidean, it looks flat. But when you sort of zoom out, you see that it's a curved surface, right? So the example of that was, for example, in 2 dimensions, we took this example. This line was going through this data. So this line is a curve. But if you look at any one region of the curve, let's say you look at this region of the curve, it can be approximated. So if you look at the data, suppose the data is like this, and you have fit this curve to the data. Now, the way, instead of thinking of it with all those algebraic equations, sum squared error, and so on and so forth, a much more intuitive way is simply to think of it that you have passed a smooth curve through the data. Are we together? And this smooth curve, at any given region, if you look at it, small, tiny region, if you're a little ant, it looks like a plane, right? That's sort of baked into the definition that it is smooth, right? So in other words, if you, at any given point, if you look at the unit vector that's perpendicular to that point in the surface, this unit vector keeps changing direction. Here it's different, here it's different, here it's different. And it's a different geometric intuition we are developing. Right? So now I will stop here. Okay. And for arbitrary reason, I took it up. It could have been pointing down or something like that. So you can see that as you take this vector that remains forever perpendicular to the curve. So as you move along the curve, as you go from A to B to C to D to E to F to G to H, the vector, orthonormal vector is called, the word is a unit perpendicular vector. The word is orthonormal vector, or more briefly, just the normal vector. It keeps changing direction smoothly, isn't it? Now, this generalizes to higher dimension. What is a curve here in two dimension? In 3 dimension, it would become a surface, right? And one special case of the curve is if the unit vector remains, if the unit vector at perpendicular vector, this remains exactly remains the same, it points in the same direction. Wherever you are on that curve, that can happen if and only if the curve is actually a straight line or a plane, isn't it? The definition of a linear, a flat plane, or a line, or a hyperplane is that if you look at the unit vector, or the unit vector everywhere would be the same unit vector, it would have the same direction. Are we together? So now the intuition will carry. And so these kinds of surfaces people often call manifold. There is a more technical definition of manifold that gets into a little bit into measure theory. We won't get into that. But for our purposes, a manifold is just something which doesn't have creases, right? So something like this is not a manifold because it has a pointy place where it is not smooth. It is a crease, right? It's a non-differentiable point, and just a smooth surface will, roughly speaking, call a manifold. And for machine learning, that is good, right? So now the intuition is that there are only 2 things possible. Either the null hypothesis is true. So the null hypothesis would say for this data, for example, here, is there any line or curve or any kind of curve or line, straight line, which is a special case of a curve, that approximates the distribution of this data? Okay? You would agree that there is no such thing, right? Because there is no underlying relationship. So for example, this could be the stock price of some company, let's say X. And this could be the number of penguins who at that moment are jumping into the sea. The sea from some island or from some glacier. So one can plausibly believe that one is not related to the other, isn't it? So here you would say null hypothesis is true. There is no relationship. And this is generally true. You have to ask yourself, is there genuinely a relationship? But when a relationship exists, it shows itself geometrically by the fact that your data points don't occupy the entire like for example, it's a 2-dimensional plane, right? 2-dimensional plane. They don't occupy the whole of it, or they're not uniformly scattered everywhere, but they tend to be, they don't have to be uniformly scattered, but they're sort of isotropically distributed. In all directions, they are more or less similar distribution. They won't be like that, but they will be clustered around or very close to some embedded manifold, something in there. Like for example, this curve is sitting into, this red curve is sitting in 2 dimensions, right? The curve itself is of course 1-dimensional. It's the bending of a line, but it is sitting there and all the data is proximate to the curve, isn't it? It's close to the curve. And so one way of defining regression and all that we have learned from a pure geometric perspective is we are trying to find that manifold, a generalization of a surface, basically a surface, smooth surface, that is closest to all the points. So imagine that all the points are pulling the surface towards itself. Each point is pulling the surface towards itself. Now the sum total of attraction from all the points, what will it do to the surface? It will make it at the equilibrium state, or the place that it will stabilize would be the solution to your regression problem, isn't it? And there is a very interesting actually intuition that comes up. When you use the sum squared error, you use remember, you use the residue square, then the intuition almost is like this, that if you imagine springs, from each point there is a spring that is connected to the surface of the curve. It is literally pulling it towards itself. And as you know, I mean, this is a very basic fact of school physics, that the force by which the spring will pull this line towards itself, or surface towards itself, will be proportional to the distance. If this is the r, it will be proportional to r squared. It's sort of an intuition that the further apart the point is from the surface, the harder, quadratically harder it will pull towards itself. Right? And in the case of a linear, absolute error, sum of absolute errors, it's a linear pull, like twice as far will just pull twice as much. Right? But in any case, you can think of it as attraction, that all the points are calling the surface to come near it and pulling it towards itself. And the surface will therefore bend. And imagine that your surface is flexible, right? So it's like your aluminum foil. You can sort of bend it, right? And it will take the shape of your data. And this generalizes to higher dimensions, to any number of features. So one way you can remember in a geometric way is that linear regression is the search for that surface in the data space that is closest to the data, such that data is just proximate to it, hovering around it. That's one intuition. So we'll carry that intuition forward. And now we will do a different class of algorithms. Any questions, guys, folks, by the way, with this intuition before I move forward?
Wait, can you repeat what the vectors for each point are? Like, what quantifies the strength by, like, that each point pulls the surface toward itself?
Distance. See, you remember that the sum squared error, if you remember, what is a sum squared error? It is summation over I of all the residues squared. Sum of residues.
Okay.
Now, if you think of a residue as the displacement of a string connecting a point to the solution, then you realize that this is a measure. This is a measure of how strongly that point is pulling the line towards itself, or the curve.
Oh, okay. Okay.
And it sort of maps to the intuition of a spring very strongly. The further apart it is, the more strongly it will pull. Right?
Yep.
That's sort of a physical intuition you can carry to go with this geometry. Now, we will now move to another class of algorithms that are called classification. So this is the week of our classifiers. Classification is the process that we will do. What is classification? Classification is actually quite interesting. The example that I gave initially when I spoke of classification is or the story was that you have taken children to a meadow. There are cows and ducks there. And you are asking a child, what animal is this? Is it a cow or duck? And the child has only two choices to say either it's a cow or it's a duck. And this process of taking an input, an animal, and saying that it is a cow or duck, identifying it is classifying it. You say cow is a class, duck is a class, and the category contains just two classes, cows and ducks. You have to choose between these two classes. Why do we call them classes? The reason we call them classes is because ducks is a class. There are many, many ducks. They all may differ from each other. But there is a notion, there is a conceptual notion of a duck that the class represents, right? And likewise for the cow, there's a conceptual notion of a cow, right? So for example, your notion of a duck would be a small, feathery, beaked, webbed feet, little creature. Your concept of a cow would include features or attributes like big with a swishy tail, horns on its head, and 4 feet, right? Those would go along with your intuition or your conceptualization of what a cow is. Are we together? So this process of classifying or identifying the class from a whole finite list of classes or a category, it is called classification. It goes beyond machine learning. Some of the oldest theories of human knowledge have posited that to know something is to be able to identify its attributes and understand the attributes and identify it as one of the known things. Right? So if you look at the speculations, for example, going to the oldest school, perhaps the oldest school of Indian philosophy, which is the Sankhya philosophy, in the writings of Kapil and so forth, a statement like this is made that all of human knowledge is, you cannot gain knowledge unless you, from memory, you can say that, when you see a cow, you have a notion, attribute of a size, you have the attribute of a hoof and certain attributes. Right? These things, they help you identify it as a class of animal called cows. Right? But if you were to encounter an animal whose attributes you have never encountered, one of the philosophical thoughts is, how would you even know it is there? Your sense organs are trained to pick certain features from the external reality. Your eyesight picks certain attributes. Your nose picks odor, smell. Right? Your skin perceives touch. These all provide you some feature of this unknown object in front of you. Because you can perceive it through your sense organs, and your sense organs have evolved to perceive this small subset of features of that external reality, it helps you identify what it is. And that identification is to put it in a class that your mind, somewhere in the memory, you have the notion of a cow, you have the notion of a duck, and therefore you can identify it. So the speculation, or one of the theories, is that much of human knowledge presumes memory, right? And it is the interaction between your external reality or data that your sense organs bring, and a mind is a classifier that immediately classifies it and puts it into the right bucket, which is there in your memory, right? Which is there in your mind. It's classification. Right? So this is what classification is. We will formalize this speculation or this way of thinking by saying that suppose you have feature vector x1, x2, x3, and it could be, for example, the size of the animal, then whether x2 could be the weight of the animal, right? X3 could be, what should we say, whether it has the size of the beak. So obviously, the size of the beak for a cow would be 0, right? Perhaps. I'm just taking perhaps not the best features, but you can imagine a set of attributes that the child will learn to identify. Maybe you'll educate the child and say, do you see a beak or not? If you don't see a beak, then it is not a cow, it's a duck. Right? Things like that. So educating a child the concept of a cow or duck is very similar to training a machine learning algorithm, a classifier. So you give these meaningful attributes, these feed into, so this we can represent. By now, you must be familiar. So you can represent it as a vector in n dimension. So let me say this is m dimensional space. So m dimensional input feature space, right? And what do? You then feed it into a machine. This machine will say either one of these things. It will say cat or dog. Cat or, well, no, here, not cat and dog. The one that we took is cat and dog has become cliche, so I'll use duck and cow. Are we together? Right? It can give this, and it will identify it as duck or cow, but it can do as an intermediate stage. It may also say probability of a duck. It may say, hey, you know what? I'm never sure. It is not a binary answer that it is a duck, it is a cow. I may say that I believe it is a degree of belief. In a Bayesian way of thinking, probability is the degree of belief. Right? So you say that my degree of belief that it is a cow, let's take cow as the positive step, is something 0.9. So then your degree of belief that it is a duck has to be the complement of that. It has to be 0.1 because it can either be a cow or a duck, isn't it? So your machine can produce either a probability, and then from the probability, you can set a cutoff. Yeah. So let me break it down into 2 steps. You can say that I have a box and an input vector goes in, which stands for x1, m features, the m-dimensional input vector. It goes in. This classifier first produces, what it really produces is a probability of a cow. Right? It produces the probability of a cow. But then what you can do is you can apply a threshold. You can apply a way to break apart and say, well, if P is greater than some threshold, the most intuitive way you may say in this particular case is, let's say, a 50%. Right? If your degree, if it is more than 50% or more, then you say it's a cow. Else, it's a duck. So you chose a threshold from a probability. Right? Now, I will pose a question. I chose the middle point of belief. Right? If your belief is stronger that it's a cow than that it's a duck, you go for cow. Right? Is this a good way of doing it? Can you conceive of a situation where you would want to put the threshold, identifying it as one thing or the other, not like this, but as something different? I'll give you a minute to think about this. Anyone?
Hey, here you're assuming that x1, x2, all of them have equal weight.
Oh, those are inputs. So
yeah,
it doesn't matter, they're inputs. And internally, this machine knows what importance to give to each feature. So assume that this classifier is insanely smart. So let us for the time being take this classifier to be insanely smart. Right? For the time being, so don't focus on the inputs. Think of the output probability. And we are taking the threshold that if your belief is stronger that it is a cow, then it is a cow. If it is, then your prediction is a cow. If on the other hand, it is less than your belief that it's a duck, then it's a duck. So that means at probability 50%, you make a decision. Is that a rule that we should always follow, or can you think of a situation where that would be a bad idea?
So I say, does it depend on the input, right? You're assuming that you're feeding only cows and ducks, right?
Yeah, these attributes are about cows and ducks. So this is example, but think of a different example. So for example, you could say, I am trying to predict whether I'll have a punctured tire when I go driving today. Let's take that example. So you go and look at the tire, the tread, you scratch your head. So one input is the tread on the tire. The second input is what kind of rough surfaces you'll be driving on this trip. And then now you're trying to determine to what degree you believe that the tire will puncture. So you have to say it will puncture or not puncture, right? Or it is like, what would you do? Change the tire or not change the tire? That's your decision. So where would you put the threshold?
No, but that's not the same thing, right? Because here it's not whether it's cow or not a cow. It's a cow or a duck.
No, so assume it, take it as a binary thing. If it is not a cow, it is completely equivalent to it being a duck. Assume that. See, this is not a trick question. Fixate on that. Fixate on, think about the threshold. Can you conceive of a situation when the threshold should not be 0.5?
Like for the car example, wouldn't you want to be like beyond a reasonable doubt that your car tire won't explode, because it would be far better to have a higher threshold so that you're more sure that your car tire won't explode. So you
That
can
is
set a
right.
higher threshold.
That is right. So what we do, for example, with cars is, if we have even a 20% probability that you're likely to have a puncture, your decision would be change the tire, isn't it? So you would put a threshold, depending on your risk tolerance, a pretty low. Even a 20% chance would make you do that, isn't it? On the other hand, if you want to give, if you want to determine whether somebody should, okay, let me give a few examples and you guys tell me where the threshold is. These days, we all go through cancer screening, right? If you reach my geriatric age, then there's a special set of screenings that you go through to look for this or that cancer in the body, age-dependent scans. Then if you are a woman, then one of the big dreads is the breast cancer, and so on and so forth. So suppose you're going through a screening test for breast cancer. And let's say that there's a machine learning algorithm that is automatically evaluating the X-ray, the DICOM image of that X-ray, the digital image. And it comes up with a probability that you may have cancer. At what level would you send the person and say, there is an anomaly, there may be an anomaly worth investigating? Where would you set the threshold, high or low?
Low.
You would set it very low. Even you would say that even if there's a 5% chance or 3% chance, depending upon how good your accurate your machine is, with very low probability, you would want to do that, because uncaught cancer evolves rapidly. And then the later you catch it, the worse it is. The worse, the harder it is. The cost in terms of both human suffering and in terms of the hospital care needed financially, it rises astronomically as the cancer progresses. Right? So you want to catch it early with the least doubt that it may be cancer. You want to mark that case as positive for cancer, because what will happen is that is the screening test. That person will be scared for a few days. The doctor will put the person through some other tests which are much more precise, a much more expensive and accurate test. And then it will turn out the person may not have cancer, doesn't have cancer. So it was a temporary scare, which is an acceptable amount of thing, rather than letting a truly cancerous patient slip by, isn't it? Telling a cancerous patient that they don't have cancer. Right? So you want to put a threshold very low. Let's take another example. Suppose you have saved money for your kids' college education. Right then, a very good friend comes and says, oh, I am bankrupt, right? I lost my job, I lost my house, I lost everything. Can you please loan me, take an amount, $100,000, whatever you save for your college education. I will definitely return it as soon as I get onto my feet. And I'm pretty confident I will be on my feet within a year. So you want to assess the probability. Suppose you have a machine that can tell you the probability that your money will come back in a year. At what threshold of probability would you typically be willing to give the money that you have kept for your kid's education? Because if that money doesn't come, your kid will not have a college education, right? So at what threshold would you, of confidence or belief, would you be willing to lend the money?
High, right? Like 50% or above.
Yeah, much higher, much higher.
No, very higher, minimum 95.
That is right. It depends upon how close the friend is. So you would put the threshold high, isn't it? And so where you put the threshold depends on a case-by-case basis, right? That is a lesson that we were trying to bring about. Right? So now that we have a basic idea of a classifier, we will go into the sort of mistakes a classifier can do. Let's take the example. Let's take, well, we took cow as the positive case, or maybe cow may not sound to you like a positive case. Let's take the example of cancer, right? It's a morbid thing to consider, but we'll consider that. Suppose your machine is saying, I have this probability that the person has cancer. And you have, let us say that you have actuality, actual positive, right? Positive and negative. So let us say that you know you are in God mode. You happen to know that there are let's say that there are about 10 positive cases and 90 negative cases. Let's take a number for the sake of argument. And let us say that you make a prediction. Positive, I'll put a prediction as a hat. Is that okay? For the sake of brevity, right? So how many positive cases were identified as positive? Let us say that I mark it as, for whatever reason, your tool is not too good. You got 3 of them right. How many negative cases you detected as positive? Let's say that was, you got it, you went and scared 2 people, right? How many positive cases you predicted as negative? Well, if they are 10, it has to be 7, isn't it? They have to add up to 10. And likewise, 98. How many negative cases you got as, well, 88, sorry. 88 you got as negative. So this kind of a matrix where you put, the actual answers when you are training an algorithm, and this is your classifier's predictions. There is a name for this. It is, for very intuitive reasons, called the confusion matrix. Are we together? It is called the confusion matrix. Now, which part of this confusion matrix is a good news part? When would you say the classifier is doing its job well? For this part and for this part, isn't it? Those are the positive cases. It did identify as positives, right? And these are the negative cases. It did identify as negatives. What would you call this? A negative being marked as a positive, it is a false positive. Because this is not really positive. Your prediction is a false positive. Would you agree with the language? It's a false positive. 2 false positives. And then, what is much more serious is, so you go and scare 2 people. This is the false negative. Right? Does this, is this language making sense, guys? Any questions here? So this confusion matrix, is the root of a lot of measures that people have. I will write a few of those down. One of them is accuracy. Accuracy is the proportion of correct, proportion of right. Correct. Predictions. So looking at this, what do you think is the proportion here? Anybody would like to venture a guess? What is our accuracy?
91 divided by 100.
91%. 91. Right? So it is a 91 over 100. And therefore the errors, what is the error rate? Which is the opposite, which is the proportion of errors.
9 by 100.
It is 9 over 100. Right? And so now comes quite a few other measures. At this moment, I'll park them because I'll give some context later and then talk about it. Those are called precision, recall, and there. So you will see a lot of jargon associated with it. There would be things like sensitivity, and what is the other one? Oh, specificity. And I'll explain mathematically what each of these means. Specificity, and people also talk about the type 1 error, type 2 error. And the reason there is so much of vocabulary is because these things have been used in statistics for a very, very long time in very different branches of knowledge. And so they have all developed their own vocabulary. But at the end of it, they are all derived from the confusion matrix. This is the ground truth of what happened. This is what really happened with the classifier, right? And its predictions. And the confusion matrix is the thing that tells you how well it worked. And from it, you derive all of these other measures. Are we together? So these are model diagnostics. Let me now introduce you to another interesting model diagnostic. It is called a very interesting name. It is called ROC, receiver what is it? Operator curve. I think I got that right, receiver operator curve. Correct me, today I'm a little bit tired. So when I'm tired, I start mixing up these little things. So anyway, ROC curve. But ROC curve intuition is quite beautiful. Where it comes from is this. So imagine that, this thing actually comes from signal processing. Imagine that you're sending a signal here through a channel. So you're sending zeros and ones. Right? You have the sender. And here is a receiver. And just for a moment, think how signals are sent through a wire. If it is a copper wire, right, you would send typically a high voltage and a low voltage, isn't it? A high voltage may signify a 1, a low voltage will signify a 0. And so you send the zeros and ones through the pipeline. Let's say that the high voltage is 1, like let me just say 1 volt, and the low voltage is 0 volts. Now what will happen is, as the signal goes through the wire, what will come out is not necessarily a perfect 1 volt and 0 volts. You will notice that because of the noise in the channel, at the receiving end, things start getting garbled up, right? Somewhere along the line, there are all sorts of transformers, amplifiers, whatnot, right? And you're never able to transmit through copper exactly this sort of a wave. It will start smoothing over and things will start happening. So you will start getting voltages, different voltages like 0.6, 0.3. What do you do with these? Right? You need to determine what you would do with this. Should you interpret 0.6 as 1? Should you interpret 0.3 as 0? It seems likely if your threshold is half, right? But what will happen is, based on, and let's say that it's pretty noisy, after a little while, your system gets pretty bad. So now, imagine this situation. The worst case situation is that all the, the one, this channel has pretty much destroyed, it is at capacity or exceeded the capacity. You may send one, what you will get out at the other end is can with equal probability go to 0 as a prediction or 1 as a prediction, equal chance, right? And likewise, the opposite of 1 is 0. It may go equally to 0 or to 1, right? So let us say that we create 1 as the positive case, high voltage case. When should we mark the signal as 1? At this given time, when you sample the voltage here, you see a certain value, should you mark it as 1? Right? So what will happen is, let's make this very interesting plot. It is called the false positive rate. And here, the true positive rate. Now, if this channel is absolutely useless, there is no real information being transmitted. Anytime you want to increase the true positive, like you want to identify all the ones as ones. One easy way not to miss the ones is keep your voltage threshold at which you say it is a 1, high or low. If you set your voltage threshold close to 0, anything above that 0.001 volt, you mark it as 1, right? What will happen? Will all the ones get identified, the true ones get identified as ones, right?
Yes.
But what will happen to your false positive rate? Zeros will also get identified as, most of the zeros will convert over because they will shift a little bit to higher voltage and they will start showing up as well. So you will have a very high false positive rate. I mean, very high true positive rate, capturing all the true positives, will also cause a very high false positive rate. So now you say, well, that is not something. So you increase the voltage a little bit. You say my threshold is now, let's say, a little bit higher. So now, again, some zeros will get interpreted one way, some other. But let's go to the other extreme. If you go and set your threshold, voltage threshold at 0.99 volts, now what will happen? Your true positive rate will be close to 0 because all the ones are getting pushed down a little bit in voltage. So none of the ones are being interpreted as ones, isn't it? So you have true positive rate will go to 0, more or less, very small. And the false positive rate will also be 0 because, if something was 0, very unlikely that it will be interpreted as 1 because very unlikely that the voltage fluctuation would be so much, isn't it? Or something like that. Or maybe it is. So this is the other extreme, right? And you can think through and realize that if you increase the threshold, like if you bring the voltage down a little bit and set the threshold there, then the true positive rate will increase, but false positive rate also increases because some of the zeros are now getting interpreted as ones, right? And so there's a linear relationship. So if this is 1 and true positive rate is 1, like we are talking fractions, this diagonal line is the line of a channel that loses all signal, isn't it? What comes out as a voltage has no relationship whatsoever to the input. Would you agree with that? Right. Now, on the other hand, let's just say that the signal is fairly clean. Let's take the other situation. You have another nice channel 1, 0, 1 and 0 goes in. Let us say that 1 gets diminished to 0.9 volts, 0.75 volts, etc. And 0 at most gets pushed to 0.1 volts, 0.2 volts, right? There what will happen? And very, very rarely a 1 will get, occasionally, because some glitch in the system, it may suddenly become 0.1. So you may still have some error rate for 1, right, as it passes through. And for 0, occasionally, just by happen chance, you might end up with 0.7, 0.8 or something like that, right? So the channel is pretty clean, with just a little bit of noise. So there what happens? You would have, if you set a threshold, let's say you set the threshold to something very modest. You set the threshold to 0.6 volts or 0.7 volts, right? At 0.7 volts, what will happen? Your true positive rate will be near perfect, isn't it? Because the ones did not get pushed down to any further below that. The lowest value you see here is 0.75. So your true positive rate is very high. But what about your false positive rate? Very small proportion, very tiny proportion of the values will actually become, ones. So what will happen is, at a very small value of this point would be, you would achieve a very high true positive rate. Now, this point, by the way, is constant, which is that if you set the threshold as absolute 0, then even the zeros are becoming 0.1s. So then your true positive rate and your basically you will have a pretty bad situation. Right? So what you do is, no, sorry, if you set it at exactly 1 volt, exactly 1 volt, because this represents 1 volt, then all the 1 volts are being slightly depressed. What is your true positive rate? 0. Right? Then false positive rate is also 0, even in a good channel, isn't it? So what happens is, as you go and bring the voltage a little bit down to 0.7, your performance of your channel goes like this. It saturates very, very quickly. And because there is still some noise in the channel, it goes something like this. Are we together? That that this is pretty much at this much is the sustained error rate. If you can tolerate that error rate, you get a pretty high true positive rate, right? So this is the signature of a good channel. Is the physical intuition clear, guys? Any questions? If it is not clear, I'll repeat it. Right. So in other words, a good channel, you can set threshold reasonably, and very quickly you reach pretty high true positive rates without the false positive rates going up. Right, as you can see. So this curve has been used in this industry for quite some time, I suppose. Now, coming back to our situation, what is the equivalence to it? If you think of a classifier, the input to the classifier, you know the ground truth. You know whether a person has cancer or not, because it's training data, isn't it? So you know whether it is 1 or 0. But you are feeding it through the classifier, and the classifier is producing a degree of belief that it is cancer or not, a probability. That probability is again between 0 and 1. Do you see how the two situations are equivalent? Isn't it? So a thoroughly useless classifier will randomly put numbers. So it will be like the noisy, hopelessly noisy channel, right? It will follow this diagonal line. Whereas a very good classifier will be able to distinguish the patients with cancer from the patients without cancer. And by having a very small false positive rate, you still get a very high true positive rate. Most of the cases you're catching. Are we getting the point, guys? So this this thing, the way you distinguish it is you say that how do you mathematically now represent this geometry, this intuition of a curve? The way you do that is you look at the area under the curve. The area under this curve is, well, if this is 1 and this is 1, what is the area under the curve, under this useless channel curve or the useless classifier curve? What's the area? If a triangle has a base,
Half.
half, exactly. So what happens is that the area of, it is called, let me call it a dummy classifier, which is just making random guesses, is 1. So area under the curve, under the curve for a useless classifier is the straight line type, isn't it? But for the red person, also the area under the curve of the red classifier will be closer to 1. Sorry, this is half. Sorry, I should have corrected half, 0.5. My error. This will be closer to 1. So, for example, this could be 0.85 or something like that. The better the classifier, the higher the area under the curve. Right? The higher the red area under the curve. In the good classifier, isn't it? So there is a term for this particular metric. I want to say the term is area under ROC curve. Oh, by the way, I got this. Now I remember it is not curve. Receiver operator characteristic curve. Characteristic. So this is ROC stands for this thing. ROC curve stands for receiver operator characteristic. It speaks to the channel, right? So area under the ROC curve, therefore, is a good diagnostic measure of your classifier. Another good diagnostic measure, just like accuracy, error rate, precision, recall, sensitivity, specificity, etc. All right, somebody had a question.
Yeah, Asif, so like in this curve, we are showing, I mean, the area under curve, we are showing a false positive rate, not the actual, I mean, the true positive, right? Or
the true positive is along the y-axis, the false positive is along the x-axis.
okay, so in the case of like cancer, Asif, like because the threshold will be very less, it should be, I mean, this curve should go bad, right? I mean, it should go very down. Why it should go up?
So in the case of cancer, what you do is you want to catch all the true positives, right? So where will you put your threshold? You don't mind a high false positive. You look for the saturation point. If it is not moving, you see at what point you reach an asymptote, right? Or saturation. Once you know that you're reaching saturation, let's say here, this point, right? You would consider this the acceptable nuisance, I suppose, error, because you want to make sure that you have as high a true positive rate as possible, isn't it? You catch as many people with cancer as possible.
Yes.
You look for a saturation point.
Okay.
So this is this measure is actually one of the very reliable measures of a classifier, and it needs a lot more explanation than just the ones derived from the confusion matrices. And it has all to do with where you set the threshold. So in a classifier, like in a simple form, we say that a classifier is a box where X vector goes in and out comes an identification, a cow or a duck. But it's a two-step process. Take one of them as a positive case, probability of a cow. Then on that, impose a threshold. And based on where you impose the threshold, you will have a certain false positive rate and a true positive rate. And you have to decide based on real world situations, what is acceptable, isn't it? You would make a determination based on that. Right? This is how it works. So probability, and what is probability? There are two interpretations. So let me take a moment to talk an aside on probability. You notice that I keep saying probability is the degree of belief that it is something. Right? There are two, actually, it turns out that the word probability is differently interpreted in two schools of thought within statistics. One is the frequentialist and one is the Bayesian thinkers. The two, and both of them are right in their own different ways, or more practical. Well, there's no right. Each definition works well in certain situations. The frequentialist definition says that probability is nothing but the proportion in a lots of trials. What does that mean? Proportion of lots of trials. Lots means really lots. So for example, if a coin, let us say, is biased, you keep on throwing it. You throw it once, it comes out head. You throw it twice, it comes out head. Would you say that the probability of a head is 1? You wouldn't say that. It may be just fluke. Now you keep on tossing it. When will you know that the probability of head is, let's say, 40%? Heads come up only 40% of the time. And it was just a fluke that twice the head came up in the ring. One way is that you keep on tossing the coin gazillion times. And then you see what proportion of the time it came out. That is the probability of the head. Are we together? That is the frequentialist. To the frequentialist, probability is proportion in lots of trials. So I'm deliberately using colloquial language to get the intuition across. Lots of trials. Are we together? Right? So for example, quite often you have taken the weight or the height of, let's say, 1,000 people, and you have built a histogram. One easy way to do probability is to just divide the histogram, the frequency plot, scale it down by the number of people, scale it down by 1,000. So you will know for each weight bracket, what proportion of people fall in that weight, that height bracket. Right? And so you say that is the probability that a random person would have that particular height. Does it make sense, guys, the intuition? Right? So that is the frequentialist way of doing probabilities. There is actually an alternate way, which is belief and degree of belief that something is true. So for example, we have global warming, human-caused global warming. Now, what is the probability that we are screwing up the earth? Right? It's a belief based on some scientific evidence, right? So at this moment, there is no very direct causal thing. The chain of causality is not that strong that you can say, look, this equation tells you that we are causing global warming. It's a very complex phenomenon, right? So all we can do is look at all the evidence and have a belief, degree of belief. That degree of belief, if you think about it, it sort of is also something that will go as a proportion from no belief at all, right? So if you talk to one group of people, they will assure you that maybe the PR department of fossil fuels will assure you that there is no human causation of global warming, right? Human activities don't cause global warming. Then you can have the other end of the spectrum where somebody may be absolutely convinced that we are causing global warming, right? So the second person's belief is to the point of certainty. And you go between back and forth. So if you say no belief at all as 0 and certainty as 1 and all shades of belief in between, belief that human beings are causing global warming, you realize that you will realize after a little bit that it follows the same rules as the rules of probability. Are we together? Right. So, and we won't go into that, but I'll lay it out as a fact. The same probability of A plus B, if they're completely disjoint, that the probability of A times probability of B happening, and so on and so forth. But leaving the mathematics aside, we'll leave that. So why is that belief? When you consider that belief as probability, there was a very uncomfortable situation historically. Remember, I told you about that wonderful statistician, data scientist, Fisher, who flew in from London to argue that it is not smoking that causes cancer, but cancer that causes people to smoke. Remember, we talk about that fellow. So he was actually a great statistician who contributed many, many ideas. One of the ideas we'll talk today is called maximum likelihood estimation. He was a dyed-in-the-wool frequentialist. He believed that that's the only way to interpret probability. And he looked at this whole belief-based, or this what he would call Bayesian thinking, as utter nonsense. So because he called it utter nonsense, literally in the 20th century, for many, many decades, Bayesian reasoning was outright dismissed. Until a lot of scientists from physical sciences, physicists in particular, mathematical physicists, they started coming into this field, and they were inherently Bayesian because everything is a hypothesis and a degree of belief there, right? So then the whole thing was revisited, and today Bayesian probability is definitely very legitimate, and we take it to be true. And in fact, the tables have turned when we bring in the whole Bayesian approach. It turns out that in the frequentialist, in a pure frequentialist world, some things had become dogmatic to the point of being wrong, right? So you will often find jokes saying, one meme that I found on the internet, very funny. It said, move all the statistics books to the, what was it? To the mythology section, because that's where it belongs. It's not facts, right? Implying that much of the statistics that was done in the 20th century was actually wrong, right? And so there's lots of thinking around it. It wasn't that the theory is wrong, but its application, the way people were using even the frequentialist statistics, had deep flaws. For example, there is something called a p-value, right? It is a measure, it's called the measure of statistical significance. Now, you may have noticed that I went through chapter 1 to 3. I asked you to review in your textbook. But when I was teaching you, I did not emphasize p-value very much. A p-value is very much baked into the frequentialist way of thinking. It is a valuable measure, but Bayesians don't tend to get, well, they use it cautiously, let's put it this way. But it was abused a lot. So what would happen is you would create some theory, you would pull up some data, and if the p-value was more than 5%, you would say my theory is correct. There's a relationship. A lot of theories with nutrition and medical research of the 20th century had to be thrown out, and we have thrown them out. People have revised all those theories. When you look back at the paper and see what went wrong, it turned out that it wasn't that frequentialist theory is wrong, the statistics is wrong, but the way people in a very cookie cutter way used it and made rules like this and make claims using that was deeply flawed. So there was a huge backlash. And today, many papers, many journals, they prohibit you from using p-value itself as evidence of a theory being right. Right? So now we are in a different world, in the 21st century, the tables have done. So there's a Bayesian way of looking at it. Let me give you an argument for the Bayesian. Again, this example, we have global warming caused by humans. It is or it's not caused by humans. If you look at the people who are arguing against it, so quite often the arguments are silly. But if you look for the legitimate ones, they all come back to one state. Where is the evidence? What are they asking for? They're asking for, in effect, if I have to interpret that right, do this abstract experiment. Let humans do whatever they are doing. No change of behavior. Wait 100 years and see, did the world destroy itself or not? Let's say it destroyed itself. Then say, oops, right? Now immediately go into somehow restore the earth, rewind somehow, restore the earth if you could, and let this trial run again. And this time see what happens. And keep on going it. If most of the time the earth gets screwed, you can say, well, you know, we are heading towards disaster. There is evidence. On the other hand, if most of the time the earth just self-heals itself, and then whatever we are doing doesn't matter, right? The evidence, you have to run the trial quite a few times. At the end of it, if you look around at the legitimate things, it boils down to that. Where is the evidence that humans have caused? Where is past historic data, essentially? We have indirect data, causal data, physical laws and other things are there, but not that. But the Bayesian way of thinking is sometimes you get only one shot. Like for Earth, we don't, to the best of our knowledge, have the ability to rewind in time. If what is done, it's an irreversible process. The arrow of time is irreversible, isn't it, to the best of our knowledge? So you don't get to do that trials. What you have to do is, based on everything you know, all the data, you have to weigh it and come up with a belief. When you do that, you may have a prior belief, but seeing the evidence, your belief may change, right? For example, suppose I land in a city at night, and I have no idea which city I landed in. And I may believe that I've landed in Arizona during the summer. I've landed in Arizona, let's say Phoenix or something like that. But next morning, I look out of the window and it's raining, right? That should displace my belief. I should feel a bit less sure that I'm in Arizona, because it rarely rains there in the summer. But it may be one of those rare days. Now I stay there the next day and again it rains. That should diminish further my belief that I'm in Arizona. Do you see how it goes? Data takes you from a prior belief to a posterior belief. And in fact, machine learning, or much of science, is this journey from a prior belief to a posterior belief. And the statement is, if you have enough data, it doesn't matter what is your prior belief. Enough evidence will always take you to the same posterior belief, isn't it? But if there isn't enough data, then of course it is better that you took a sensible prior belief, right? So instead of believing that you landed in Arizona, pick a place that's halfway, that where it rains sometimes and doesn't, right? And then start from there, or something like that, you know, or then revise your belief. And then if it keeps on raining every day, you might finally accept that perhaps I've landed in Seattle, right? Things like that. So that is the thing. So I wanted to bring this once and for all, that probability at its heart itself has two interpretations. But now I'm going to use one of them to make the argument, to introduce two more concepts. One is surprise, right? So bear with me, guys. So we will say, how do you quantify surprise? Right? Or let's put it this way: how many exclamation marks would you like to put in your what is that? I am emoji or whatever it is that that people call it when they work on the mobile devices, right? Their cell phones. So how many exclamations? Right? So let's try to quantify surprise. Let us say that you know that it rarely ever rains in the desert, right? You are in a desert. Let's say you are in some place, pick Sahara Desert, right? Then evidence comes. The evidence is today it did not rain, right? Data is data is it did not rain. How much is the surprise? Because the probability of rain, actually, let me call it probability of no rain. If I may use a negative here, probability of a dry day, rain-free day, a dry day, is in the desert, it is close to, let us say, 0.999, right? Or even 1, why not? And then it did not rain today. How surprised are you? Would you be surprised? You wouldn't be surprised, isn't it? On the other hand, so in this example, you would not be surprised. But suppose the probability of, if the probability of a dry day is this high, what is the probability of rain?
0.001.
It is 0.0001, right? So it is, the Q is for the rain, P is for dry. Well, suppose take the contrafactual. You wake up in the morning and lo and behold, you notice that monsoon clouds are over there and it's raining. Now, how surprised are you? You are very surprised, isn't it? So now look at this. The probability, when the probability of something happening is low and it happens, you have a high surprise. When the probability of something happening is high and it happens, you have pretty low surprise. You think, all right, that's it, isn't it? Does it agree with our intuition, guys? So now take our common sense intuition and try to figure out how would we write it as mathematics, right? So you can say that, see, can it be proportional, surprise? Can it be proportional to, by the way, can it be, this is the proportionality symbol. Can surprise be proportional to the probability of a given event happening? Can it be? Then will it be so that when the probability is high, the surprise is low? That doesn't agree with it. Right?
It should be inversely proportional, right?
Yes. So one way you
1 by
could,
P.
yeah, you could do, well, you can start by saying maybe, so earlier, let's take this journey. So this seems like a bad, right? So the next thing you could do is, well, let's see, let's try better. Maybe you can say, let's try, and there are many ways you can do it, but let me give one of the simpler ways. You can say, well, what about 1 over P, just like Hari said. So do that. So mark it like that. Now what happens when probability of something is low, 1 over probability will be high. So 1 over 0.0001 will be a big number. So this we seem to like, right? Better, right? But then it has one problem. If the probability of something is 1, what is the surprise? Well, it turns out you're still surprised, because what is 1 over 1 is 1, whereas really surprise should have been 0. It would have been better if the value was 0. Are we together? Is this making sense, guys? You want an expression that would give 0 surprise when the probability is 1 and high surprise when the probability is very low. We are getting close, except that we seem to be lower bounded at 1. So whenever you have information that is lower bounded from 0, 1 and going to infinity, so it is like this interval, 1 to infinity, there is actually, there are many ways to convert this to a scale in which it truly goes from this range, it goes to the entire 0 to 1. One simple trick is you say surprise.
1 by P minus 1 by 1 by P.
So let's try 1 by P minus 1 minus 1 by P?
No. 1 by P minus 1 whole divided by 1 by P.
1 by P whole divided by P. Let's try that out. If the probability of something is sure, you could say it is 0. But when the probability of something is very low, then this would start bothering you. So this is one way that you could do that. There is actually a name for this. So Hari, it seems that you have taken a statistical course. So I would advise you to, at this moment, help other people make guesses. So there's a name for it. It's called the odds. In statistics, we call it the odds. Right? Odds. What are the odds that something will happen? And if you ever watch the news, you may have noticed that these newscasters never speak in terms of probabilities. They always say the odds of somebody winning. And the odds go from 0 to infinity, isn't it? So that seems to be one way of doing it, right? But there is another way that you could do that. That I would like to bring here. You could do it like this. Take the log of 1 over P. And there's a deeper mathematical reason. I'll come to it. Why not this, but this? When you take log of 1 over P, you will see that it has the same effect. When P is 1, log of 1 is, what's the log of 1?
0.
0.
0, right? So this will now go from 0 to infinity. So this gets the job done. And there are other mathematical expressions that you can do, transformations you can do by a probability that will get the job done. There are infinitely many things.
Well, if you have log of P, that will also give you the same thing, right? If P is 1, log of P
Okay,
is 0.
let's work it out. For P is equal to 1, log 1 over P is equal to log 1 over 1 is equal to log 1 is equal to 0, right? On the other hand, for P is equal to 0.001, let's say, you're doing log of 1 over 0.001, that is equal to log of 10 to the power 3, isn't it? And that is equal to a positive number, right? Let's say,
Yeah.
based upon, if you're doing base 10 or base E. Let's say, actually, you always do log E traditionally, right? But if you were to cheat and say log 10, well, it will be 3.227. Okay, let's say that it is 1,000 would be, I don't know, 7. I'm randomly putting some number here. It is probably equal to that. Right? So you can check it out if you have a calculator. So it is now a positive. You're seeing this, right? And the smaller you make it, the more it tends to 0, the more the surprise increases. It tends to 0, surprise tends to infinity. Raj, you're seeing this, right?
Yeah, it makes sense, right?
It makes sense. So now, why would I pick? So you realize that this is a legitimate way for me to capture surprise, isn't it? Well, odds, why not this expression? Or why not any other mathematical function that will also do this? Well, there is a deeper reason for it and a lot of thing. This surprise that you just saw, right, log, it is related to the concept of entropy. And we will come to that. The average, so suppose you do a long-running experiment, right? And sometimes you see this, sometimes you see that. Right? What will happen is the average surprise that you will get, averaged over all the outcomes that you see, and we can do a little bit of a derivation to show that, it is actually a P times, so I'll give you this. Let's say that you sat there in that desert for 1,000 days. The probability of rain is 0.01, right? And let us say that, so how many days did it actually rain? 10 days. So 10 days you had huge surprise, and a lot of other days you had very little surprise. So what is the total surprise that you encountered? the total surprise that you would encounter is for the days that it rained, the proportion, and you would agree that the proportion of days it rains would be literally P, right? A P times this log of, because the surprise, how often were you surprised? Effectively, if I were to multiply it by 1,000, the probability, I will come to know the number of times that it rained, isn't it? 1,000 times P is the number of days it would have rained, basically, give or take. And each day that it rained, I got this much surprise, right? And then for a lot of other days, 1,000 times Q, which is 1,000 times 1 minus P, this would be the number of days, dry days, isn't it? Approximately. Let's say 990 days it didn't rain. When it didn't rain, you were very mildly surprised, isn't it? The surprise was very mild. So you would say when it didn't rain, the didn't rain probability was Q. So you would say 1,000 Q log 1 over 1,000 Q, right? And so the total surprise is this. Total surprise is this. And when you take the total and divide it by you take the average surprise now, divided by the total. So in average, what is the surprise? It would be this total divided by 1,000, isn't it? Total over 1,000, and that would cut out the thousands, and it will leave you P log 1 over P plus Q log 1 over Q, because these many times you'll see this. Are we together? Proportion of times that you will see this. And literally what you're looking at, this is called the entropy, actually. This is this expression. So if you were to, like, each of these pieces is actually entropy. Entropy. So entropy is defined. So one more measure, entropy, which is a measure of average surprise for something happening. So average surprise for it raining, which is the positive case, is a P log 1 over P. Right? Now, in the literature, you don't really see entropy expressed in this intuitive way. Typically, in your books, you will see entropy mentioned as minus P log P. Right? Actually, well, it's P log P, but in the machine learning literature, you look at it like this. Right? You look at it like this. P log P is the entropy, and this is the negative part of it. Actually, so this is not, well, not exactly entropy. Entropy is P log P. Okay. So this part is the entropy part. Right? And so the total surprise is the negative of that, average surprise. Right? You see it like that. But remember that intuitively, it's much better to think of it as this. Right? This is the surprise. This is the proportion of surprise. Right? Gives you the average surprise. And that gives you the intuition. So we created another measure that we have. Now, when you do it like this, now ask yourself, suppose you did a machine learning. So far, are we together, guys? I know it's been a long session. Before I take a break, I'm almost near the end of this long intellectual journey. So imagine that you have a box, a classifier. You know the ground truth, whether it's a cow or a duck. So, and you want to create an error function, right? One way of writing the error is literally the error rate. The trouble is with the error rate, you can't do gradient descent. It's a number, how many times you got it wrong. You need an expression that is mathematically amiable so that you reshape the probability, the output, says that it does the best classification, isn't it? So you want to be able to do gradient descent. So you need something that has the probability baked in. And therefore, it turns out that using this negative P log 1 over P, the surprise is a good way of thinking about the error. Think about it. It was a cow. Cow is the positive case. But your machine predicts probability of cow is 0.9. What's the surprise? Ah, yes, close, isn't it? But you know this is a cow. But your machine predicts like 1/10 the probability that it's cow. It has a strong belief that it's a duck. Now, how much is your surprise? If you believe that your machine is right, you should be terribly surprised, isn't it? You have a high surprise. And so now we are getting somewhere. This surprise, which is written in terms of probability, and therefore it is somehow derived from the input data, the way it learns from the input data. You can fudge your probability predictions based on your data set. You can do gradient descent and find ways to make better probability. Now you're coming to a measure, error measurement that makes sense. So this sort of error measurement in machine learning, even the sum squared error and all of this, there's a general term for it. These are all called loss functions. This is a measure, in the simplest form, it's a measure of how wrong you are. Are we together? And the amount of surprise you are, if you are in the, if you know the ground truth and you keep seeing the predictions of the machine, you would be surprised if it makes wildly wrong predictions, isn't it? So the more the loss. If you add up all the surprises, that is a good candidate for the loss. Are we together? That is why, so let's say that this is your, for each of the outcome that you have, let's say that the positive outcomes are, whatever the positive outcomes are, pi, you will do log of 1 over pi, summed over all the positive cases. I belongs to positive case, right? And you would also add up all the surprise belonging to the negative case, isn't it? The negative cases log 1 over, well, what is the probability of it not being a cow? It would be, would you agree that this is the probability of the negative case, right? Q. And so the loss function, this is, and this long journey has taken us to a very interesting notion that a good loss function for classifiers is loss function for classifiers is this. So this is for the binary situation, right? Positive and negative, right? So it is summation of I log 1 over pi plus summation over j log of 1 over 1 minus pj, right? And so in this thing, people try to be clever. What they do is they say, notice the fact that positive ephema. So here is a little bit of, so this is the way you should remember it, guys. And always think of surprises. Classifier losses are a measure of surprises. If you carry this intuition, you'll always remember this expression. Otherwise, you'll tend to forget it. Now, here comes the thing. Mathematicians can sometimes be clever, just to write things in a more succinct way. So if you take the case, positive case as 1, right? Like you say, cow is identified as 1, and duck is identified as 0. So you can write this as 1 times this. So now let me just rewrite this. Summation I log 1 over pi. And see the trick that you do. I'm perfectly okay to put a 1 here, isn't it? When it is genuinely a cow and positive or belonging to positive cases. And when it is a duck, this is again 1, but I can write it as 1 minus 0. Right? Now, why in the world would I do something so fun? You'll see in a moment. This. You say, well, where am I going with all of this? Well, remember in machine learning, we use the literature that we call Y the label. These are the labels or ground truth. Isn't it? This is the ground truth, isn't it, guys? So this expression is I belongs to a positive case, yi, because all of this positive case yi's will be 1. It's like literally multiplying by 1 log 1 minus. Now 1 minus, what is pi? This is the prediction, right? Y hat. Your classifier's prediction is literally the probability by definition, right? Because what is your machine emitting out? Probabilities. Degrees of belief that it's a cow. Are we getting it? And that is the y hat. Y hat being always in machine learning, whatever it emits out, whatever it predicts, we call y hat. So your y hat is there, 1 minus yi hat. Right? This plus summation over negative cases, j belongs to negative case. And oh boy, this part was again yj hat. So for negative cases, 1 minus yj, so not yj hat, it's the ground truth, yj. And of course, yj is 0, right? For ducks, the label is 0. So 1 minus yj will make it 1, right? And this is just mathematical cleverness, guys. The reason I'm mentioning it is we'll do the opposite journey in your mind. And this is yj hat, right? This expression now is the end of the intellectual journey. We said that the loss, cross entropy loss, let's write it in cross entropy loss, implicit word is function, loss function, is equal to this thing. Are we together? It is this. Now, log of 1 minus yi is, what is that? If you do log of 1 minus plus, it is yi. I'll convince you that it is this. See, log of surprise, the surprise, 1 minus yi, the prediction, I can write as log 1 minus log yi hat. Log of 1 is 0, and so this is equal to minus log yi hat. Does this make sense, guys? Right? So in literature, you'll always find it mentioned like this. In your textbook, you'll find it mentioned like this: yj log y 1 minus y, sorry, 1 minus yj log 1 minus yj hat. So typically, now it's one of the things that typically books will often write this expression in this form, and then you feel sum squared error was so easy to understand. This expression looks, if you were to encounter it, you would wonder, where is it coming from? So now I've given you, hopefully, an intuition. So whenever you see this in your mind, never remember it like this. Like, how do I remember it? I actually remember it like this. The version that I remember in my mind, I tend to remember it like this, because I like to carry the intuition with me. Otherwise, I feel uncomfortable. So this is, to me, more intuitive. It is basically surprises. Right? The model has made prediction. You compare it to the ground truth and find the total surprise you went through. That is your loss. The same thing after a lot of, mumbo jumbo, it is the same thing as this. Right? But let me just say more intuitive. Okay. More intuitive.
Asif, I think the second one also should have negative sign, right? In the cross entropy loss, it's not
right.
plus.
Sorry. Yes, that is true. Plus, what I forgot to do is that in both the cases, take the minus sign out. In both of these cases, there is a minus sign. Good. This is right. And if you break it up, yes, you have negative sign everywhere. Right? So you can write it as minus yi log yi hat minus 1 minus yi hat yj log 1 minus yj. Now you say, well, this is believable, but of all the loss functions, why did we take this loss function? I'll let you ponder over the mystery. Could we have taken something else? Right? You notice that we went through a very interesting derivation. If you know the concept of a surprise or entropy, then maybe it is obvious. But I don't know if you have, those of you who have taken other machine learning courses from elsewhere, if you have encountered this sort of explanation. But this is more intuitive way of looking at it. But you could think of other ways. There is actually a justification, a more rigorous justification that comes from MLE, maximum likelihood estimation, and we'll talk about it after the break. Let's take a 10-minute break. It is 8:44 by my clock, so we'll come back. I'll pause the recording. Where is the recording stop? So just let's summarize what we learned from here. Surprise is, we chose to define surprise as log 1 over. Then entropy is essentially the measure of average surprise. Like P proportion multiplied by surprise after each of the events in a trial would give you this. And it's traditionally written as this, is a more traditional form of writing it. And cross entropy loss function for a classifier, which is making predictors, looking at the ground truth and comparing it to the predictions, how surprised would be, and that is given by this expression. And I also said that while this expression, to me at least, looks a little bit intimidating, I like to think of it more simply as like this: I belonging to the positive case, log y, log 1 over y hat plus summation, no negative, plus j belonging to negative case, log 1 minus yj. Right? This is the same, it's just in my mind, I prefer this way. Simpler way to remember. Positive case is 1, negative case is 0. So any questions here before I continue?
As if it will be yj hat, right?
Oh, sorry, I forgot the hat. Thank you. So guys, thanks. Please keep correcting me. I can be quite sloppy and careless. Is it all making sense, guys? So now the question comes, why did we use entropy? Why? Or why not odds? Why not something else for the loss? So let's get the easy ones out of the way. Why not use error rate? Well, you can't do learning with error rate, right? Because error rate, you have imposed a threshold, then make a number prediction. You can't do gradient descent in that. Right? It gets hard for many reasons. Now, why not? So there's another subtle reason. Why not this thing? At any given moment, why did we not do y minus hat? Because whatever the probability is of it being a cow, and it's a cow, I can look at the difference between the two, isn't it? And I can square the gap. Why not sum squared error? Why not do the same thing here? And the answer is a bit subtle. The answer comes out that in the case of a classifier, it doesn't, first of all, your loss surface is not convex. So you have difficulty doing it. It's not stable. It doesn't quite work well. But there is another reason that comes from, which is a more rigorous reason. It comes from a maximum likelihood estimation. So let us say, so let us define a concept called, the next concept we will define is likelihood. likelihood. What is likelihood? We know what a probability is. Likelihood is given by the symbol n. Likelihood is a short form of likelihood that a given hypothesis, likelihood of a hypothesis, given hypothesis is producing the evidence, namely the data. In simple terms, the data. So I'll give you an example. Let's take two hypotheses. I will take hypothesis H1 that the probability of rain is equal to 0.1, right? I will take hypothesis 2. It says the probability of rain is 0.9, right? So these are two hypotheses. Now I ask you this question. Suppose the data is this. Let me put the data, part the data here. Data. Let's take 5 days worth of value. So what should we do? Rain, dry, rain. Let us say that the evidence came out to be this. Now, what is the joint probability of this happening by hypothesis 1? Probability of rain is 0.1, 0.1. Probability of a dry, according to hypothesis 1. Okay, so let's go through this. According to hypothesis 1, the first rain, 0.1. Second day it rains, the probability was 0.1. The third day it is dry. The probability according to this hypothesis is 0.9. The third day it again rains. The fourth day again it rains. Isn't it? So according to hypothesis H1, the joint probability of seeing this evidence, this data, this what actually happened is pretty low relatively, right? Compared to this situation. Here, the joint probability that it actually rained was 0.9 times 0.9 times 0.1. This was the dry day. The 0.9 times 0.9. Now, which of the two hypotheses looks more probable? Which has higher probability? The second, isn't it? The second one. Second one beats the first one hands down by a factor of almost 9,900. Well, 9 times 9, 81 square, whatever that comes to, right? By a huge amount, by a huge factor, it beats the probability. This. So, which is but suppose you have many more hypotheses, H3, H4, and each of these things, these joint probabilities are called likelihoods of the hypothesis. Right? Given the hypothesis, the joint probability of seeing this event, because these are independent events, so the basic probability theory, if you remember, if two events are independent and both happen, their probability, joint probability is the product of their probabilities. So I multiplied those numbers together. This is a sort of high school probability, right? So, and even if you have forgotten the probability, let me put it in a very real way. Suppose the probability of your tire being punctured is 1 in 1,000, right? And the probability for getting a speeding ticket also is 1 in 1,000. You get a speeding ticket every 3 years, right? 1,000 days. So what is the probability that on the same day you'll have a punctured tire and you'll get a speeding ticket? You realize that it is very unlikely that both of these will happen. It's the product of these two, right? So it will be 1 in a million. Right? You multiply these two probabilities, unlikely probabilities together. So that is joint probability. Right? So this is it. Now, the concept of, if I ask you of all these hypotheses, which of the hypotheses would you consider the best hypothesis to use for classifying? Which of the hypotheses? So there are many hypotheses. What criteria would you use to pick the hypothesis as the best one, as a model to predict the data?
The maximum one.
The maximum one. What you would do is, you would say, what you have is, for each of these hypotheses, H1, H2, Hn, you have a likelihood of that hypothesis. H2, L, N, right? And what you are doing is find the max of this. Max of H1, L, H2, L. So the hypothesis, actually the right word is argmax. That hypothesis, find that hypothesis, which let's say L, H, N. So find which of the hypothesis leads to the maximum likelihood, maximum value of the likelihood, isn't it? So that is the concept of maximum likelihood, right? So the traditional word for hypothesis is, because if you use that hypothesis, you can use to predict, you can estimate. Given input, you can estimate the output, right? So that way. So I would use the word maximum likelihood hypothesis in my very sort of peculiar way of thinking. But the traditional word used is maximum likelihood estimator. Right? That hypothesis, which leads to the maximum likelihood, is the right hypothesis. So you're most likely in Seattle and not in Phoenix, Arizona, right? If this is the data, that is the most likely to produce. So make predictions. If you make predictions using the model, and if this is truly representative of the population, rather than just the sample of data is representative of the population, you would rather pick the hypothesis that you have landed in Seattle rather than landing in Phoenix, Arizona, isn't it? So now let's take this thing, this hypothesis business. Suppose the probability of rain is P. Is this. The probability of dry, I call it Q. Q by definition is 1 minus P. Right? So now let's use, instead of 0.1 and 0.9, let's take this. We don't know what P is, and therefore we don't know what Q is, because Q is just 1 minus P. Suppose you see this evidence, a particular evidence, which is that rain, rain, dry, rain, rain. So what would you say? This is the first data point. 1, 2, 3, 4, 5. You would say probability 1, right? Given this data, whatever the conditions of that day were, right? Pressure, temperature, etc. Suppose input variables are temperature, wind speed, pressure, right? Humidity. These make your X, right? These are your X1, X2, X3, X4. And so you can go on. This goes in to your box. What comes out is a certain P, probability function. So you can use that probability function to the first data, to the second data. But according to this has to be Q3, isn't it? Q3, right? And P4, P5. This is the likelihood. This is the likelihood of this evidence, right? Likelihood of R, D, R. Would you agree? This is it, right? So now let's generalize it to all cases. Now let's go beyond rain and so forth. Suppose you get data, it's cows and ducks or whatever it is, and you get thousands of data points. So you need to create a likelihood function, which would literally be all the positive cases, right? Multiply. So what are you doing? You're multiplying all the positive cases and you're multiplying all the negative cases, isn't it? So a PI, the product of all the PIs, I'll use this symbol to imply P1, P2, P4, P5. This stands for product, right, in the language. Just like sigma stands for summation, this stands for product. This, so this, let me write this. Likewise, a product of Qj, well, in this particular case, it is just Q3, right? And so it is basically, you would write it like this, isn't it? And therefore, your likelihood function is likelihood of this hypothesis P is product of all the PJs for positive, PIs, I for the positive case, and product of all the, well, in this case, there is one, but suppose there was another dry day, all the negative case, Qj. So I hope this agrees. This is all I've done is rewritten common sense as an expression, as a more succinct expression, isn't it? And you would agree that you want to pick that value of P that maximizes L. Each of the probability is a hypothesis, right? Probability value is a hypothesis. So you say that maximize, find P that maximizes LP, right? LP, and probability is, of course, because it's the output, it is a function of the input. Somehow it is built, the classifier has built it out of the input, right? It's some function of the probability has to be some function of the input, right, for it to be meaningful. So you need to maximize this, right? And thus, how would you, to maximize this? So you need to maximize this product. Now, a couple of things come about. This way is good in theory, but it is problematic. Problem is, probabilities are small numbers between 0 and 1. So whether P is 0.1 or 0.9 doesn't matter. If you get 1,000 data points, the product of 1,000 numbers between 0 and 1, what will you get? You will get a number so small that your computer will think of it as 0. Right? Because computer has a limit of how small a number it can understand. And so you will become smaller than it. So that doesn't seem very useful. Mathematically, it's right. So there is a trick you can use. What people do is they say, all right, let's take the log of it, log likelihood. Log of the likelihood, right? Because if log will make it additive. So now it becomes I belongs to the positive case, log of Pi, isn't it? Plus J belonging to negative case, log of Qj. Is it beginning to look suspiciously like something we have done before? Now the thing is, you need to maximize this, max this. But it turns out that most of the numerical computation libraries, they are designed to minimize things, not maximize it. So how do you convert this to a minimization problem? Very easy. Suppose if you have to maximize this, equivalent to minimize the negative of this. Minimize minus log likelihood, right? Likelihood of Px. If I do this, maximizing this is the same as minimizing this. Do you see the guys? Eh? Maximizing the log likelihood is, I can either do that or I can minimize the negative of log likelihood. The bigger the log likelihood is, the smaller the negative log likelihood. Are we true? And therefore, that is nothing but minus of this I belonging to positive cases, log Pi minus log, well, what is Qj? J belonging to negative. Q is, of course, 1 minus P j, okay? And this, and what was this? This was the original log function, loss function we took. It was a measure of supplies. Do you see that, guys? Huh? So this is actually a more formal definition or derivation of a good loss function, okay? Which is exactly the same as what I gave to you with a more intuitive notion of supplies. Okay? This is your loss function like this. Right? And of course, you can reformulate it in my language by saying, forget the minus. You can absorb the minus and say I log 1 over pi, right? Plus summation j log over 1 minus pj. Isn't it in my language? You would do it like that, thinking in terms of supplies. And of course, PIs and PJs are predictions. So now you can translate it back to the equation. So we went through a long derivation, guys. This is a very important derivation. It's a foundation, and it hopefully gives you a justification of why we took the measure of surprise to be the log, and we started with that rather than some other mathematical function, isn't it? Now you may ask this question, something is suspicious. Maximizing the log is the same as minimizing negative log, but are we sure that maximizing the likelihood function is the same as maximizing the log likelihood function? Is it really true? Well, it turns out that that works, because if you look at the log of numbers, it is, I hope I'm getting it right, it's a monotonically increasing function. So as x increases, log x also increases, isn't it? Do you see that? The log function, if you remember from your basically high school or middle school, it looks like this. So it is justified. Maximizing a function and maximizing its log are equivalent, right? And so maximizing the function is through all this derivation the same as minimizing the negative log likelihood, right? And that is the loss function that is used for all classifiers. Now, so let's summarize. Once again, we get back to the same summary. This is what you need to remember: surprise entropy, cross entropy, that is a loss function. And I've given you two derivations of this, right? One of the reasons I gave this derivation is usually this derivation is missing in books. Sometimes the book will have the maximum likelihood argument. The maximum likelihood argument goes back to the same Fisher, the statistician who argued that cancer causes smoking. I think we'll never forgive him for that, isn't it? So, so now you say, all right, this is good, but we haven't actually learned of a classifier. How would we classify? Let's do a real world example. Okay? So one of the first classifiers that you will encounter is the easiest classifier. Right? It is called the dummy, or it is also called the 0R classifier, or the dummy classifier. So let me illustrate it with a story. So imagine that there is a valid doctor who actually has degrees and did graduate in the better half of the class, right? Near the top of the class, and hasn't forgotten his stuff, learned from experience. And there is a quack, right? You can have your pick. All of these, chiropractors and what peculiar healings and so forth. So there's some quack. You go to the doctor, you go to the quack, and you say, oh my goodness, I am in trouble, I'm sick. And the quack gives you a pill. And lo and behold, you're fine. And you notice that people who come to the quack, he tends to give them this pill and they tend to get better. They go to the doctor and they also, That also gets better. In the majority of the cases, both of them manage to cure people. How would you know that one is quack and the other is not? Looking at the evidence. All of them got fixed, or majority of them got fixed. How would you know which guy is quack? Just from the evidence. You're not allowed to look at the degrees. What would happen is, let's say, how would the quack function? Most diseases are self-limiting. It's a fact, right? The human body has an incredible healing capacity. Right? And it is amazing, actually, how much it deals with the environmental factors, adverse environmental factors, and just recovers from it. You have a fever, you walk in the snow, you have a fever, then 3 days later, you're fine. You eat bad food, you have bacteria in your guts, and then you have upset tummy, you vomit and all sorts of things. And again, a few days later, you're fine. Most diseases are self-healing. Right? In fact, one of the great discoveries of cancer research was, I think it was made 10, 15 years ago. And from what I understand, the discovery was that actually cancer keeps, the cancerous events keep happening in our body all the time. Right? Yeah. But our body has a pretty strong immune system, and it goes and squashes it. Once again, you heal from that. You don't even know that you had cancer for very episodic amounts of time. Okay? But when there is what is called immunal escape, the cancer cells manage to evade or do something to beat around the defenses of your immune system, your fighter cells. That is when they win, because now if the fighter cells cannot kill them, they will proliferate. And so they proliferate, and it becomes, then you need much stronger measures, radiation, whatever it is, and it is recognized that you have cancer. Right? So the human body is very subtle. This is a little bit of us. So as a quack, what is your best bet? Whosoever comes, you give a pill and says, my dear boy, you'll be absolutely fine. I assure you, just take this. And most of the time, he'll be fine. Let's say that 1 in 100 actually has serious disease that may lead to any kind of morbidity or mortality, right? But most of them, they become right. So this person, how often is this person wrong? 1% of the time, right? So for the quack who has no information, has no clue of medicine, what is the best approach? What is the best thing he should say? Give people ash or something, or chalk in a capsule, and say, you'll be fine. Prediction is, you'll be fine. Isn't it? Because that prediction will be true 99% of the time. And how did the quack come to that? Because the data shows, data has 99% recovery rate, even without medicines. Isn't it? So what is the purpose of the doctor, the genuine doctor who has gone through 10, 15 years of medical training? It is to catch that one person, to be able to identify the one person who is genuinely sick and won't recover. Isn't it? So a good doctor is a valid classifier, can distinguish between a truly sick person and somebody with mild illnesses. But a quack cannot. So the quack is this is a quack, right? So first thing you do, or the simplest prediction, which is not random prediction, it is still a sensible strategy, right? You just predict all will be fine. Now we know that today it's very interesting. As modern medicines, frankly, started around the time penicillin was discovered, right? It was the first thing that could hit bacteria. Before that, if you have a wound, it gets infected, you die. Very high chance that you would die. Battle wounds would lead to death. Right? People develop infections, they would die. But doctors have been around. Most of the modern medicines that work didn't exist before the 20th century. Very few of them existed. But doctors have been around for tens of, like at least a few thousand years, if not tens of thousands of years. So what were they doing? It is a worthwhile question to ask, how were they curing people? Or were they curing people? Because all of them with great confidence were telling the patients, eat this medicine and that medicine and you'll be fine. Today, when we look back at the history of medicine, we realize that actually all this, it was a confirmation bias. What would happen is somebody would find a leaf or a herb or something, develop a lot of, would see that if you give it to the patient gets cured. And so now you have you thought it would cure the patient, and now you have evidence that it cured the patient. It's called confirmation bias. So the most generous interpretation is you get the confirmation bias builds up, and you begin to think that this really works. The only thing that was missing was a double-blind study, right? Given this medicine and not given this medicine, what would have been the chances, which wasn't done. But double-blind studies were a rigorous method that is of recent discovery, recent establishment as a scientific method. Okay? So today we know actually that most of those medicines, if you go back and look, they were silly, right? So those doctors were well-meaning, but they were not too far from being quacks. Today we have modern medicines, and of course a good doctor can cure it. Think of a good doctor as a good diagnostician, and that's what your classifier is, right? So anything better than that, dummy classifier, what should it do? Pick the majority label. Look at the Y values, the actual labels, actual outputs, and pick the majority, and always predict that, right? So if you see a preponderance of cows and only a few ducks, the child can easily fool the parent by always saying cow, 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 right? That reminds me of a lot of these people who forecast the stock market and keep saying the market is going to crash. Every single day they wake up and say market is going to crash. And the moment, eventually the market crashes, and then they have become, they write books on how they were the only people who could predict that the market was going to crash. I don't know if you have encountered such people in the financial news. Any website, go to Fools, I don't know, whatever there was.
Yes.
You find those. Right? Why? Because if you keep making the same prediction every day, of course it will be true someday, right? But the opposite of that is that you pick the majority outcome and every day say that, because majority but inherently means more than 50% of the time you'll be done.
What if it's 50-50?
Then just pick one. You have 50% right. Randomly pick one.
Randomly, okay.
Which is why you should always pick odd amounts of, just pick odd number of samples. You can pick a majority. Right? So it's a good thing. What you do is when you get 50-50 sample, you draw another sample, right, and see what happens. Or you just pick one and you know that is it. So why are dummy classifiers? Why am I even considering? Because they are the benchmark. I need to compare every good classifier that has actually learned something to the dummy classifier. Isn't it? It must outperform the baseline dummy classifier. If it doesn't outperform the dummy classifier, that classifier is no good. Would you agree with that?
Yeah, so basically dummy classifier is like null hypothesis.
It is the equivalent, sort of like that. It is the baseline, right? How would you know? I'll give you an example. Suppose your error rate is only 1% or 2% or something like that. 1%. How people go and say accuracy 99%. So I hope one lesson you learn from this is the accuracy is a meaningless number unless you know the class asymmetry, right? What is the class imbalance? Sick versus healthy. If it is 1:99, then a dummy classifier will give you 99% accuracy. So if you see a lot of marketing and a lot of things claim we have 99% accuracy or whatever, some number, right? Those numbers, if now that you know about these things, you should always take a grain of salt, because accuracy without knowing class invariance is meaningless essentially. Because in this highly asymmetrical data, you need to do far better than 1% to be called a valid classifier, right? The error rate has to be far lower than 1%. Am I making sense, guys? That's how you do. You compare to the dummy classifier. Now, leaving that aside, we will now come to a more legitimate classifier, and we'll give the next 1 hour to it. Do you guys want to take a little break, 5 minutes break? What we have done so far is talked about classifiers in general, the theory of classifiers. Like how, 2 things we did. How do you do the diagnostics of a classifier? You look at accuracy, error rate, precision recall, the ROC curve. By the way, I remember receiver operator characteristic curve, and the area under the ROC curve, AU-ROC. Did I put that thing there? Yeah, I should mention that there's a name for it. It is AU-ROC. It is usually written like this: capital A, little u, R-O-C, capital. Right? In the literature, you'll find it written like this: area under ROC curve. ROC curve, right? And the last C is on it. Area under ROC curve. So then we created a sense of a loss function. We wanted a notion of loss function, and we started with the notion of a surprise. We did 2 derivations. One is using an intuitive notion of surprise, and we said that the loss function is simply the total surprise when you compare the predictions to the ground truth, to the labels. Right? Along the way, we encountered entropy, which is average surprise per instance of data, and then we did. So this is the summary. Then we did a different approach. We looked at the likelihood, and likelihood is something. Remember, likelihood is not in the traditional sense of probability. It is likelihood that a given hypothesis is producing the evidence, the data that you actually see, the training data that you actually see. What is a, right? The full form of a likelihood is that, if you remember it like this, that likelihoods are associated with hypotheses, whereas probabilities are simple probabilities, right? So you look at it like that. Then you're looking for that hypothesis that is maximizing the likelihood of the evidence. Right? And that approach is the maximum likelihood estimate approach. Right? And then we took the example of rain and so forth. And we realized that if you maximize the likelihood, you end up with products, which is great. This expression, product of positive cases, product of negative probabilities. And in theory, great. Mathematics can stop there, but you can't do that in computing. You have practical limitations. You have underflow. Things will become too small and everything will become zero. So to solve that problem, you take the log of it. Log is legitimate because log is a increasing function. If x is increasing, log x is also increasing. Right? So you maximize the log. But because numerical libraries, they are designed, most of the machine learning libraries, they like to minimize things, not maximize. Very easy. If you, instead of maximizing the log likelihood, minimize the negative log likelihood. And therefore, minimization of a negative log likelihood is the cross entropy loss. And it turns out when we do that, surprise, we ended up with the same equation that we came through a very different route by collecting the total surprises. Then we talked about dummy classifier, which must be a baseline. So guys, many times I've seen people do this. They will write a classifier. They'll bring you a Jupyter notebook, or they'll bring you Python code and say, see, here is my model and here is the data, and look at the model diagnostics, how good it is, right? This is how most people do. The one thing they miss is the lift. The only thing that matters in machine learning is what is the lift over the dummy classifier, right? And in regression, what is the lift over the null hypothesis? How much better are you doing than the null hypothesis? Right? because that is the measure of learning. That is evidence that some learning has taken place from the data, isn't it? All right, guys. So we will learn about an interesting classifier called the logistic regression. Well, this is very poor use of terms because it uses the word regression, which is most unfortunate because it's a classifier. So you can always sit in interviews and ask, okay, what are the regressors you know, regression methods you know? People will say linear regression, logistic regression. You can end the interview right there, right? Because logistic regression is for classification, despite the name. It's a logistic regression classifier. It's a classifier for us. So we'll do that. We'll do. There's a different way of looking at it. Like, okay, we won't talk about the exponential family and so forth. So we'll do this. 5 minutes break, guys, and we'll start.
Asif, in the loss function, right? Can we make it a maximization problem of area under ROC?
Area under the ROC comes is a derivative effect after you have worked all the probabilities, right? And pick
Yeah.
a. It doesn't admit gradient descent.
Okay.
You're too far away. It is too. A much more direct thing is to work with the loss function. I mean the log likelihood itself. Amongst other things, it's a convex function, right? And as you know, convex functions are much easier to deal with.
Agree.
For simple situation, for logistic regression, for simple situation, these are convex things.
Yeah, and I forgot at the start of you told that recently the p values were not being considered as what you have to say, that where we say that generally if p value is less than 0.5 then we accept it, like the two-tail test, the stuff. Why they are not accepting it? I did not get that point.
No. See, people have abused the p-value. See here, okay, let me say this differently. In science, you can things that confirm or agree with the theory, right? The
Yeah.
more data you find that agrees with the theory, the more you believe in that theory.
Yeah.
Right? Effective theory. But it doesn't prove that the theory is correct. One single data point that contradicts the theory is enough to demolish the entire theory. It is called the Popper's falsifiability criteria. In the philosophy of science, it's a landmark position. Karl Popper, by the way, was a professor here at Berkeley. So science inherently is a body of falsifiable knowledge, falsifiable theories. Right? In a quantitative way, it can falsify, it can produce a data that will dismiss it. The only point is, like, for example, the theories that we know that have stood the test of time, we haven't found data to contribute. Therefore, the fact that we find more and more data that agrees with the theory, but never find the data that contradicts the theory, makes us believe that. That's how science works. Now, in this world, now in bringing it to statistics and machine learning, what happens is that when you find that let's take an example, your R square is good. Does it prove that your theory is correct?
No.
We realize that you also need to do residual analysis, right? If residual analysis works well or reasonably well, again, it is just adding to support. It is increasing your belief that the theory may be right or effective. Never use the word right, it's effective, right?
Yeah.
But nothing says you should never trust one metric and say my theory is right. For example, if you get very high R squared, you get very low, like your residuals look fine. You may still be completely wrong because your model may have hugely overfit the data.
Yeah.
Right? There are many subtleties in this world. So the basic thing is no one metric is proof that you are right, ever. The problem that happened is because mathematics is used in social sciences and many fields, psychology, medicine, etc. It was used with half-baked understanding. And p-value in particular became a tool of abuse. So 5% p-value, smaller than 5% p-value was often considered evidence of something happening, some relationship. And so there is actually a lovely book written, actually it's written it's a bit sarcastic, which is a negative side, but it does make strong points. It's called The Cult of Statistical Significance. P-value, the formal name is statistical significance. Read a book called The Cult of Statistical Significance. It goes into great depth on why a p-value should be used with caution. It's not that the p-value is entirely wrong. It's just that you should use it with caution. And it is very easy to abuse it. Very easy to abuse it, to such an extent that you must always have many other confirming, supporting evidence. And p-value should be just one of them. Right? See, high p-value will contradict you.
Yeah.
Low p-value doesn't confirm you.
Yeah.
It just happens not to contradict you. Right? So not contradicting doesn't mean confirming it. That's the subtlety. Guys, the rest of you are extraordinarily quiet. Is it all making sense? Is it proving interesting so far?
Yes.
Good. All right, our 5 minutes are over. I hope those of you who took a break are back. Now, guys, today will be a little bit longer session. I hope. Is there anyone who would like me to have a hard stop at 10? Most of you are at home, so it shouldn't be a problem. I'll take the liberty to go about half an hour more. Right? So let's take a situation. So let's create a story. We will take a very simplified world or data that may or may not be realistic, but it will help us learn our pedagogical learn. So we are trying to distinguish whether a fruit is a grape or is it a cherry. Now, grapes and cherries are about the same size. Well, or let's say, yeah, same size, but one is a bit heavier than the other. If I remember right, cherries are significantly heavier. And if cherries is not plausible, let's take, what is bigger than a grape? Which fruit? I was going to say blueberries, but they are smaller. Okay,
Mango.
Come again?
Mango.
Mango is huge. Okay, we'll take blueberries and grapes. How about that? Blueberries and red grapes, like the nice Napa red grapes. So suppose you have two variables, the volume or size and the weight. These are the only two features you have, x1, x2. And you have to tell, is it which fruit? Grape versus blueberry. Now, blueberries, as you know, are light and small, usually. But we will imagine a world in which there are some giant blueberries too, all right, that can compete with grapes, the tinier grapes. So you have data. Now, because it's a two-dimensional, let us plot it out. We will plot it out on the, what are the two features? Weight and size. And let us make the blueberries. Blueberries are tiny. They will exist as hopefully somewhere like data points like this. Does this look plausible, guys? Something like this. And your nice champagne colored grapes. Let's take a nice champagne by color. Which one should I take? Maybe I'll take this. This here. Because even some grapes can be small sometimes. And here are huge grapes. You're supposed to write a classifier that tells this is your data. You need to write a classifier that distinguishes between a grape and a blueberry. So one thing you could do, just visually inspecting it, it's very tempting for us to do this. Let me take a green color here. It is very tempting for us to draw a line like this. Does this look reasonable, guys? Or maybe a little bit bent down.
Yeah.
This was not the best line. Let me choose, add data points to agree with it. Now, you may have a few big blueberries. Now you notice that if you draw a line, so we will take a line in this case, because in this course, we are making linear models. Right? I will take 4 of these data points. I will call them A, let's say something like B, and something like C, and something like D. What can you say about A? How strongly do you believe this tiny little thing, light little thing, is a blueberry?
Very strong.
You would have a very strong belief, isn't it? But what about D? A strong belief that it's a grape, isn't it? And if you ask yourself geometrically, why is it? You notice that it is quite far from this line, isn't it? But the closer you come to this line at B, right? So suppose this is B. What about B? You can't be sure. It is probably blueberry, but you know, it could be also with certain degree of probability a grape, isn't it? Likewise, C may be more a slightly stronger belief that it's a grape, but it could be a blueberry too. You see this, you know, it's not a perfect demarcation between the two. There is a bit of overlap between the blueberry weights and sizes and the grape weight and sizes, right? So let us concoct a notion. We realize that the further away from the decision, from this line we have, so this line has a lovely name. It is called, for obvious reasons, decision boundary. Decision boundary. Are we together? Decision boundary. So what do you do? If I have to find out, first thing is I can compute the distance of a point, let's say point X, the distance of X, distance, obviously perpendicular distance from the decision boundary. Why am I using the fancy word decision boundary rather than a line? Perhaps you have anticipated. As we move along this course, there may be decision boundaries which are surfaces, curves and surfaces, not just a line or plane. Are we together? So the general term we use is decision boundary. One side of the decision boundary are things belonging to one class. What is this class here is? Class here is all blueberries. And the class, the other side of the thing are grapes. This is the grape territory. In the feature space, the grape territory is on one side of the decision boundary, the blueberry territory is on the other side. But you do acknowledge that there are some mistakes, isn't it? There is a certain amount of interweaving of data there, overlap of data there. But a decision boundary is a pretty good intuition for deciding. Let's take a notion. If you go in this, for no reason, if you go in this direction, northeast here, you call this the positive direction, and if you go southwest is a negative direction, because we need an axis, right? So let us say that when dx is very much smaller than, very smaller than negative, like very negative, you can be sure what is it? This is a
Blueberry.
blueberry. It's a blueberry. On the other hand, when the d is positive, dx is greatly greater than 0, surely great, isn't it? But if d is smaller than 0, but close to 0, but small, is only a small distance away from it, but small, then maybe blueberry, isn't it? For point, look at point B. This is point A, this is point D, and let's look at point C. If dx is greater than 0, but again small in size, it implies maybe grape. So is the intuition developing? What does the intuition say? That somehow the intuition, somehow probability of a grape, let's take this as a positive case, probability of grape increases with d of x. The more positive dx is, the more likely is it to be a grape, isn't it? And the converse of this is probability of a blueberry decreases with d. The more the d increases, the less likely that it is a grape, isn't it? Do you see this, guys? Is this a clear intuition? And now comes a lovely piece of art. D, what is the range of values of D? Values of dx. This, it can go from, well, in this particular case, it can go from minus infinity to plus infinity, isn't it? What is the range of values? Well, obviously, in my world, imagine this peculiar world, there are even negative weight blueberries around. Blueberries are not only small, they can even have negative sizes and weight, so then your distance can go to minus infinity. Obviously, that's silly, but hey, we are learning. What is the range of values of probability?
0 to 1.
But we know that there is a monotonic relationship. When D increases, probability of it being a grape also monotonically increases. So I will write a statement, because it shouldn't be that the distance increases anywhere and the probability decreases, isn't it? It's a very linear movement. As you go in this direction, probability of it being a grape keeps on increasing from 0 to 1, isn't it? So let me write this thing, increases with monotonically. Now we are trying to look for a relationship between P and dx that relates them through a monotonic function, isn't it? So let's go search for it. We realize that if you take probability, we already remember that if you take, now look at odds. We already encountered odds. Odds was P over 1 minus P. Probability of something happening versus probability of it's not happening. Right? People in common language talk about the 1,000 to 1 odds that it will happen, that India will win the cricket match against, hopefully, Pakistan, right, or something, right? So this is, it's called odds. So this takes on value. What is the range of values when P is approximately 0? P 1 minus P will be 0, right? Odds, i.e. odds is 0. When P approximately equal to 1, then odds, these are odds, of course, both sides, P over 1 minus P is equal to what? Tends to, for very high P, this odds tends to infinity. That is what common people say, right? Oh, there is 1,000,000 to 1 odds of this happening. I'm sure it will happen. That's how we talk in common language, isn't it? Odds. So now this is good. P was varying. P's range was from 0 to 1. Odds ranges, odds, which is P over 1 minus P, its ranges from 0 to infinity, right? We're getting close, but there's a problem. This is only the positive x-axis, positive real line, right? But distance can be negative. The whole point is that distance is also negative. Do you notice you can have, in fact, all the blueberries are sitting in most of the blueberries are sitting in negative distance. If you look at this picture, right? And all the grapes are sitting in the positive distance. So we are not done yet. We need some other trick to make it go from minus infinity to plus infinity. And once again, the knight in shining armor that comes to the rescue is the same old log function. Right? So here comes the log function on its horse, and it says, take the log of this, take the log of odds. And then what happens? What is the log of 0 or vanishingly small number? Epsilon, very small number. What is the log of a very, very small number? It is minus infinity, right? One way to see that is log of a number which is 0.000001 is the same as log of 1 over 1, 2, 3, 4, 5, 6, 10 to the power 6, isn't it? And that is equal to log 1 minus log 10 to the power 6, and that is equal to minus 6. You see that it's negative. So the smaller you make the number, the more negative the log becomes, isn't it? So the range of log is minus infinity to plus. We are getting somewhere. So could we hypothesize that the log odds and the distance, now log odds also increases monotonically. They both have the same nature. P odds and log odds, they both increase monotonically. As P increases, they increase. Right? The distance also, of course, by definition, increases linearly. Could we hypothesize that log odds, would it not be a nice theory to say log odds is equal to distance? I mean, why even bother putting a proportionality constant? Let's just say equal to distance, log odds. Then it would agree with our intuition here. It would agree with our picture here, isn't it? If we were to write it like this. Would it? Guys, have you followed the chain of reasoning? Log odds goes from minus infinity to plus infinity, and it just agrees with our notion of the distance in this particular picture. Right? As the log odds increases, the more likely it gets that you are talking about grapes, the more you're in the grape territory. The distance increases, you're in the grape territory. Right? So to say that is actually to have discovered one of the most powerful classifiers out there. This is the logistic regression classifier. Logistic. So I will omit the word regression because to me it is confusing. So I will just call it a classifier. And as you can see, I tend to use the vocabulary a little bit different. I tend to use it to be more aligned with the intuitive way I can think through it. So the theory that says that logistic regression says that indeed this will work. Right? Now, what was log odds? Let's remember. Let's fit back all of this. It says that, do you guys, by the way, guys, do you see the sheer simplicity of this expression? When you put it next to that picture, let me draw the picture again. My blueberries over here, right? And my grapes were here. And we realize that what we are searching for is a distance from the distance. This is distance. To know whether X is a blueberry or a grape, all we need to know is its distance from the decision boundary. Positive distance is must be gray, or gets more and more likely that it's gray. Negative distance, the more negative, the more you go in this direction, the more it becomes likely. Actually, let me use blue color. Okay, let it be. So the more negative you make it, the more you go in this direction, the more likely it becomes that it's a blueberry territory. Right? So imagine that you are a car starting here. If you start driving along the negative direction, southwest, you will see, imagine that you're traveling in this feature space. What will you see? You will see a world full of blueberries, isn't it? All around you are blueberries. And occasional grapes maybe. But the further you go, the more you drive, the more into blueberry territory you are. If on the other hand, you drive your car in the opposite direction, the further you go, the more solidly you are in grape territory, isn't it? And so we capture it with a very simple equation. Log odds is proportional to distance, so let's make it an equality. And this is the logistic classifier. It works. Let's now put it in a more traditional form that people see it. It is written as log. What was log odds? P 1 minus P is equal to the distance, or dx. I will just write dx. This is also often written as z, especially in neural network literature, people write it as z. So I will write z is the same as dx, right? And now we'll evaluate what dx is. And so if you write it like this, then what happens is, if you take the entire log of both sides, it becomes 1. What does it become? Exponentiation of z. Would you agree? Now, if you add the numerator to the denominator, which is perfectly allowed, what is the denominator here? 1. Right? E to the z, I can put the denominator as 1. Now, why in the world am I doing this? By the way, this is an algebraic trick. You can add the numerator to the denominator so long as you do it on both sides. Right? So this will become P 1 minus P plus P, right, is equal to e to the z 1 plus e to the z. Do you see this? And so we came up with an expression of P is equal to e to the z 1 plus e to the z. But it is more traditionally written as P is equal to probability, and obviously we are talking about x, probability of this x point being a grape. Let's bring back our notion. And suppose we divide both sides with e to the z. So e to the z divided by e to the z would be 1, and 1 over e to the z plus e to the z by e to the z. And that becomes the more traditional form, 1 over 1 plus e to the minus z. And so this is the classic or celebrated logistic regression equation. An example of this, it is, people often write it. So this is the logistic equation in its more general form, just beyond the world of probabilities, why any function that has this structure. It is called the logistic function, logit function. When you apply this to the world of classifiers, this is the same way as writing this. Now, most of the time, the books will write it like that. Now, I haven't explained what z is. I will explain in a moment, or z is equal to dx. I'm going to make a claim. Remember, distance from the decision boundary. So tell me, all points which are at 0 distance from the decision boundary, what do they do? What are they? Where are they?
They are on the line.
They are on the line. So would it be right to say that we can turn the arguments around and say decision boundary is literally defined as dx is equal to 0, literally, right? And it turns out it's a line. The line, in this particular case, the line is defined by dx is equal to 0. Now, and I'll give you a derivation of it in a moment, but take it as a path thing. The distance from the decision boundary can actually be written as beta naught plus beta 1 x1 plus beta 2 x2. Now, this begins to look interesting. Have you encountered an equation like this? When did we encounter an equation like this?
This is
Polynomial regression.
Yeah, this is regression. And that explains why people sneak in the word regression in what is actually a classifier map. The distance from the decision boundary is given by this, right? And so the full expression, your probability of X being a grade is equal to 1 plus e to the minus a beta naught, because when I plug it in here, minus beta 1 x1 minus beta 2 x2. You're getting the point now, right? And suppose they are n variables, right? This is the equation. Now, interestingly, most books, they sort of drop this equation onto your head, including your current equation. You come up and they say this is logistic regression equation, classifier equation. And the first time you encounter it, I don't know about you, but first time I encountered it, a transcendental function, my first reaction was, where did it come from? What's the derivation of this? So I hope that I've taken you through a very intuitive set of steps to reason through this, of where it actually comes from, right? How one can essentially rediscover the logistic equation, logistic classifier equation, isn't it? Now, I haven't proved that distance is equal to beta naught plus beta 1 plus beta 2, that the distance function, this is called the distance function. And this remind me that on Saturday, I start the lab by first giving you a proof of this. Today, we are past the time. So this is it. Probability, this. So what does this look like? What it looks like is, see, what happens is that if you look at the distance function, d of x, right? And you look at p of x, the p of x being this, you see an interesting behavior. Probability goes obviously from 0 to, what is the upper bound of probability? 1, right? So this is 1, this is 0. What happens when distance is hugely negative? Probability is, what is the probability that it is a grade? When you are deeply negative territory, what's the probability that it is a grade? Look at this picture. When you are in hugely negative territory,
0.5.
0.5. Why 0.5? When you are deeply in negative territory, any other answers, guys? When, let us say that you are here.
No, probability will be 0, sorry. Nearing to 0.
The further away you are from the decision boundary, in the blueberry land, the more sure you are that it is a blueberry, isn't it? The more negative the distance, the more sure you are that it's a blueberry. So the more sure you are that it is not a grape, isn't it? And so for much of this territory, here you will be in the blueberry land. But as you come closer to this point, what is the value at 0? When you are literally sitting on the line, the best line is 0.5, exactly. So this would be at 0.5. So this will gradually start rising. And when it rises, the second part of this, you're in the positive distance. So this is negative territory. This is the positive territory. And then it will go and keep on increasing, and then it will saturate, because after you have gone through a certain distance, you're practically sure that it's a grape, isn't it? Grape territory. Grape territory, blueberry territory. Now look at this curve. This is in this particular case, you notice that it looks like it's a very interesting curve. Let's look at its qualities. The no-brainer is it's a continuous function, probability, continuous curve, and therefore a function. I hope you wouldn't contest that, would you? Looking at this curve. It is smooth, not contestable, right? In other words, differentiable. Again, no brainer. Why in the world would I bother? Because actually these are good properties. It's monotonically increasing. Increasing, isn't it? It increases, it never makes a dip back, right? So for example, it doesn't behave like this. Yeah? This is non-monotonic, non-monotonic, right? And this is monotonic. Yeah, a monotone is, I don't know, something like that. And if you're into music, you would say that, you would go like that. So, well, here we go. So far, so good, guys. And it has also an interesting property. It seems to have lower and upper bounds, lower and upper saturation points. Right? And you can summarize all of this by saying you take an S, S letter. Oh, sometimes this reaches the limit of how much text I can write. And I seem to be reaching that limit. Okay, I have reached the limit. So I'm going to write here because I'm almost done with it. Let's see if it will let me write anymore. No. It turns out that OneNote has a limit of how much it will let you write. We can try to sneak past it for a little bit. May or may not work. Does it work? No. Okay. So let me write it in another page. No, what's wrong with that? It's not even letting me do this. Okay, I'm not able to write for some reason as a bug in this thing. Oh, yes, new pages have come up. So just to recap, if a function is like this is the 0 line and this is the 1 line, it is like a take an S and stretch it by its tails, tails horizontally. When you do it, you will end up with a shape. You will end up with a shape that looks like this. Would you agree? It looks like a stretched out S. This function, does it look like a stretched out S? Guys, I wish somebody was speaking up.
Yes, it does. Yeah.
Yes.
Yeah, it does, right? All such functions, that have the same property, that are continuous, differentiable, monotonically increasing, have upper and lower asymptotes. So the word that you use, the limits, that the word for the limits is in the language of machine mathematics, you say that these saturation points, there is a formal word for it that you may remember from calculus. These are called asymptotes. S-Y-M-P-totes, asymptotes. That have asymptotes, and in other words, that look like stretched out S. They are all called sigmoid functions. Sigmoid functions. And it turns out that the logistic function is an example of a sigmoid function. So now let me just mention this. People often say sigmoid and logistic function. They think it is synonymous, right? Often in textbooks it's written like that. And you have to parse through and see what is the person meaning. in neural network literature, often something like this is done, but actually it's not true. So I'll give you a homework, theory homework this time. Homework, find other sigmoid functions and discuss them in Slack. Why can we use them and discuss them in Slack? For example, could we have used any of them in place of logistic function, logistic function. This is a thought experiment. Do that, guys, and discuss it. Right? This is your homework. Are we together? So now I'll summarize very quickly. We learned about one classifier, the logistic regression classifier, or just the logistic classifier. It very well handles situations like this. Like this, blueberries and grapes. Right? And remember, a decision boundary will never do perfect separation because data is interleaved. There is overlap in the data. It's the nature of the data. Right? So when you're sitting on the decision boundary, you're never sure whether it's a grape or a blueberry. On one side, you're a little bit more leaning towards blueberry, on the other side, more grape. But the further you go from the decision boundary, the more you have. And you can capture it through the notion of log odds. Right? And log odds relates directly to the distance function. The distance function, I have not given proof of that. It turns out that the distance function is a linear equation. Why it is so will be a derivation we'll do next time. We're out of time. I would like to give the last 15 minutes to take any questions from all of you. So this is our sigmoid function. Let me see, upper and lower and upper asymptotes. Right, or saturation points. Saturation values. That's better. Right? It's a sigmoid. So we covered quite some territory today. We learned the general idea of classifiers and their loss function. Right? Number one, which is cross entropy loss. We learned about various classification metrics. I talked about accuracy and error rate. Right? Now I give you a homework. Another homework is, I said there's precision and recall. Right? Precision and recall I did not explain to you because we ran out of time. Let's make it a homework. Please go and understand what precision and recall is. We'll cover it in the lab, but it would be nice if you try it on your own first. Go read about precision and recall. Likewise, and people often talk in terms of precision recall, or they talk in terms of sensitivity and specificity, depending on which literature you're reading. Specificity. So go learn about how these are defined, and think of it simple geometric intuition. What is it trying to tell you? Right? What is it measuring in real life? So that's our homework, guys. And if possible, please review this. We are doing chapter 4 of your book. Review the logistic classifier in chapter 4 of your textbook. Now, chapter 4 of the textbook will essentially start from here. It will say this happens to be the logistic classifier is this, right? And you have to move forward. And it feels a little, at least I like to see where it came from. And this is a derivation of that. By the way, this is my way of thinking. If you think of an even more simple way to derive it, please share it with all of us. So with that, questions?
Asif, I have a question when you made that log odds equal to d of x.
Yes.
So my question was, yeah, range, it was, I agree with that range, minus infinity to infinity. But my problem was when log is 0 to 1 only, it goes to basically minus infinity to 0. Don't you think it's not an uniform distribution kind of stuff? Like let's say dx is there. Dx has equal chance of being negative and equal chance of being positive. But in the case of log, it has to be between 0 to 1.
No. You're looking at the odds. When
Yeah.
the odds are between 0 to 1, it goes from minus infinity to 0. Right? That is true. That is not a problem. It's a nonlinear deformation. Taking the log is a nonlinear deformation, right? But ultimately, you have bent it to be the range that you wanted. And it raises the question: can you do other functions? This is a curve, right? For x, log of x is a bend, is a deformation. It's not a straight linear relationship, but that works. Now, this is only one of the ways. And in fact, your homework is precisely that. You could think of other sigmoid functions and think which of them will work.
So my question was actually, since we used log, right? So we have odds that 0 to 1 only we can get to minus infinity to 0. So my question was whether it was probably equal, like.
Yes, it is. The point is that when you look in terms of the distance, right? Distance is distance. From probability, you're trying to manufacture a function which goes from minus infinity to plus, right? And one easy way of doing it is taking log odds. Yeah, it is true that when you compare it to odds, it seems that we are taking a tiny range, 0 to 1, and stretching it out much further. Whereas 1 to infinity seems as though we are not stretching it as. It is true, but at the end of it, so what? It does get the work done.
Agreed.
Any other questions, guys? All of you are extraordinarily quiet. I am beginning to fear you may not have gotten. Are you guys feedback? Is it easy to understand? Yeah, go ahead, Ravi.
Yeah, so like this is true for like two, like I mean, if you like yes and no, or like true and false, is it also true for multi-classification?
Oh yes, that's a generalization. We'll come to it.
Okay.
Multi-class classification is a very obvious generalization from this. It has to do with softmax and so forth. We'll come to that.
Okay.
That's a good question. Anything else, guys? So I did a lot of mathematics, but please review this. It's not hard. And if you find the mathematics worrying, then you can, much of today's lecture, the derivation of logistic regression, you can entirely forget. The only thing you should remember is there is a decision boundary. The further you go from the decision boundary, the more sure you are of your answer, right? And there is an equation that helps you, that captures that. And its derivation is fun to know, but at the end of the day, if you don't get it, it doesn't matter. In practical terms, it doesn't matter. In fact, I doubt most people know the derivation. Okay, that is it. And the other part is the loss function, remember, which I hope was just basic algebra. It basically says that if you look at two ways of looking at it, maximum likelihood or leads to minimizing negative log likelihood, you always take that hypothesis which the data supports in simple common sense terms. Rain, rain, dry day, rain, rain. That supports you in Seattle rather than Phoenix, doesn't it? Literally common sense writ large. That is one way of looking at it. And the other derivation comes from looking at the aggregated or collective surprise. Right? We came to the conclusion that log of probability, and your output y hat is probability, log of inverse probability is a measure of surprise, isn't it? And so if you add up all the surprises, you get the total surprise. That is a good loss function, because if your model is really good, there should not be any surprises. It should make predictions very close to the true value, isn't it? That's that. So that is another way to come to the same expression, same loss function. So, all right, folks, at this moment, I will end today's.
One last question, Asif, like how to use the likelihood in real scenario, like because this like multiple, it's like voting, right? Somehow.
No, please say that again.
So this likelihood is there. It's like somehow it's like voting, right? Multiple people votes and like whichever is like higher like probability multiplication, it is winning. So how we using in the real scenario?
Yeah,
It's
so
like
the log likelihood is like if you take log of each term, because that becomes pretty much the surprise element.
I mean like multiple data point. How we
Joint, the right word you use is joint probability. The joint probability of independent events is the product of probability of each of the events in isolation, right? So for example, if you go with the hypothesis that today it rained and it has no impact on whether it rains tomorrow, these two are independent events. So if 2 days it rains and there's 90% chance of rain, the likelihood of seeing that data is about 80%. The product of the two.
okay.
So the right word you use is joint probability. Let me write that down. Joint probability of independent events is the product of their probabilities. Probability of independent events is the product of each event's probability. In a more mathsy terms, x1, x1, x2, xn is equal to the product I is equal to 1 to n of probability of xi, right? Or in simple terms, it is independent probability of x1, probability of x2, probability of x3, probability of xi. This is just saying it in a succinct mathematical way. It's the same thing.
Okay.
Any other questions, guys? All right, then, in that case, closed.